client server, and recently more on ADAS and also for AI purposes. So our project is focusing more on the generation 6 of PCIe due to the changes on the signaling schema for PCIe. Since generation 6, we are utilizing PAM4 signaling. That gives us reduced voltage amplitude on our signals for our eye diagrams. That leads to higher data rates. It's more susceptible to noise. You have way worse signal-to-noise ratios. We're dealing with 16 different signal transitions, much more inter-signal interference, and our equalization maps tend to be more complex since we are dealing with a much more complex diagram to equalize for. So, for proposed solution, we are actually continuing the work of a previous paper that was headed by Carla Lopez, which she is with us in the audience too. So on the original work, the design for a multi-stage CTLD was cheap, although the DFE is included into this design. There was not much emphasis in optimizing for this DFE block. It was just implemented as a 16-tab DFE. And also we utilized for the MATLAB simulator software, we utilized the adaptive mode for the DFE block on MATLAB. So there was not much emphasis on optimizing for the DFE, it was mostly for the CTLD. So for this work, what we have achieved is to focus a bit more into the DFE block, as well as trying to work with the entire circuit. That means that we are also optimizing some CTLD parameters and even some FFE parameters on the design that we shared on the previous slide. And just for a quick reminder of what we're trying to achieve with the equalization, we're simply trying to make it so the signal, as you see on the graphic on the bottom, we're just trying to make the signal the more equalized that it's easier for the receiver to read. So we are adding some emphasis on the transceiver so that the receiver can get the signal correctly after any losses from the channel. So for our formulation, we created a bit of an innovative parameter to optimize. Normally, when you have all the one single eye to optimize, you can build a optimization algorithm, an objective function based on, say, the area of that eye. When we're talking about PAM4, we have the three different eyes, the upper, mid, and lower. And so there's a decision-making process to select each one of those three eyes to optimize for. In our case, what we did is to build a sort of worst-case eye, which is built from the smallest eye width out of the three eyes and the smallest eye height out of the three eyes. This gives us pretty much a worst-case scenario for every simulation, and so that provides us with a much better result once we achieve a final optimized result. Our formula is pretty simple, but after we try to maximize for that eye width and eye height, we also apply a few penalizations. These are actually related to the PCI agency specification that says that the linearity has to be more than 85%, and also the vertical light closure has to be less than 6 decibels. So we have these as sort of a guard band to discard any results that we receive that may have a good eye area, but they do not comply with these specifications for PCA Generation 6. We just add a bit of a weighting factor to all these entries so that we have equalized results, and you can start to build an optimization based on those values. Obviously, our optimization is based on minimizing, or in this case, maximizing for those eye height, eye weight values that we are using. Really quickly, so the part of the reason why we are utilizing the SM optimization for this optimization effort is based on the complexity of the search space that we are working with. For our previous work, we were, as I mentioned, only optimizing for the CTLD stages, which happen to be only integer values. Pretty easy. It's a pretty small search space in comparison. When we started work with the DFT specifically, we have values from minus 0.7 up to 0.7, and these are real values. So we limited only to 4 decimal points, but we still have a much more complex search space than compared to only optimizing for the CTLD values. And as I mentioned, we are also adding FFP, transmitter FFP values as well as part of the optimization. Since we are already working with complex values, we can also add these as well to work with the entire circuitry for the optimization effort. Now, once we apply this optimization technique, we can compare the results that we had in our previous work with the results of this current work. For example, we are referencing here, these are the results that we had on our previous work with a DFT block that consisted of 16 tabs. We can notice we do have an eye diagram that is working correctly. We have our 3 eye diagrams. Not pictured here are the actual values for the eye height, eye width, but they did comply with the PCI Gen 6 specifications, same as well for the eye linearity, the vertical eye closure, everything was within specification. But what we could achieve at the end of this optimization algorithm, where we also try to optimize to reduce the amount of the DFT tabs that we are implementing into our DFT block, we could achieve actually better results when it came to the eye height. And obviously we are achieving this with a design that is utilizing almost half of the amount of tabs on the DFT side. You can see here the more precise results between the 2 works. As you may notice, we have very significant increases from the previous work, which is to the right, versus our current work here, which is to the left. Usually around 250 and more improvement on that eye height, while we are still maintaining values like the eye linearity and vertical eye closure as well. Just quickly for the conclusions of this work. So our proposal is to build this optimization algorithm for PCIe Generation 6. We believe that this is a very important tool that could be utilized for the industry. We as engineers, we may have seen a lot of optimization work done on perhaps just tuning for a specific amount of tabs on a design that's already placed in stone, but perhaps adding a new stage to optimize the amount of metal we are implementing into our circuits could be part of the PLC process for new products. We have achieved, as I mentioned, a very significant decrease in the amount of metal, the amount of tabs that were implemented for the DFT block. That allows us to, we're not able to get specific numbers, but this would lead us to believe that we have, for example, lower power consumption, definitely possibly less footprints on the design. Although this work we have built it completely on MATLAB, utilizing the service toolbox, this can be built on pretty much any software, both to handle the optimization process and to handle the simulation. Things like Python to work the optimization problem, and Keysight ADS, for example, as a simulation base could also work. I encourage you to explore this as part of perhaps an investigation for your studies or an investigation for your companies could be beneficial for adding to your workflow. That is all that I have for the moment. Thank you very much for your attention.
Okay, session is open for questions. Questions? There, one there.
So who performs the execution of that the values, or who and how much time does it take to equalize the system?
Let's see, I don't believe we have the backup slides. The simulation is done entirely outside of the context of a platform. This is all done in Brazilian, so this is not set up in a specific technology just yet. It was more of a proof of concept of, as I mentioned, perhaps a new stage in the PLC that we could add to improve our designs before we finalize on the amount of tabs, and then after we finalize the amount of tabs, we can start to think about tuning the tab values for that certain amount of tabs. And so the software, as I mentioned, is still pretty much in the air. It could be any software to handle the simulation side, handle the optimization problem, and any software to handle the simulation. So KeySight ADS, Service Toolbox. Perhaps if you're thinking about handling optimization on the EM side, things like Sonnet, for example, could work. It's pretty much open for much more investigation to be done.
What is that? The tab station should be set by someone writing the real plan. I understand that this is simulation, but you get keys and get them.
Oh, right. At the end, once we have decided on the amount of tabs, the next step is to extract the optimal values of the tabs for that certain amount of minimal tabs, and that can be shared with the BIOS teams to be added as part of the BIOS configuration for any specific product.
Questions? No more questions?
Okay, I have one question. You just made that. Is there any other platform that you use?
As mentioned, MATLAB was just an easy tool that we had access to. Easier since we were already working with the Service Toolbox, so we didn't have to deal with connecting two different softwares to handle the problem. MATLAB also has the Bayesian algorithm already implemented as a function, just made it a bit easier for us to focus on more on the investigation side of things, more so than trying to implement this in a very specific environment. As I mentioned, there's a lot of flexibility in selecting whichever software is more convenient for the investigation, for the company, to handle the optimization problem, and whichever software is either adequate or easier to use for the simulation of the software.
Another question? No more questions? So, thank you.